Welcome back to the London Futurists podcast. Some people say that all that's necessary to improve the capabilities of AI is to scale up existing systems. That is, to use more training data, to have larger models with more parameters in them, and more computer chips to crunch through the training data. However, in this episode, we'll be hearing from a computer scientist who thinks there are many other options for improving AI. He is Alexander Ororbia, a professor at the Rochester Institute of Technology in New York State, where he directs the Neural Adaptive Computing Laboratory. I had the pleasure of watching Alex give a talk at the AGI 2024 conference in Seattle earlier this year and found it fascinating. After you hear our conversation today, I hope you reach a similar conclusion. Alex, welcome to the London Futurist podcast.
Thank you for having me.
Thanks for joining us, Alex.
Alex, before we turn to your current research, can you tell us what led you into the study of AI?
A really long time ago, when I was a young engineer, I was exposed to something called philosophy of mind, and that launched me on this pathway of particularly thinking about identity. I was fascinated by this notion of what does it mean to be yourself. Obviously, this has entanglement with concepts in consciousness, which is really, really complicated and interesting. And I was always fascinated by this notion of identity construction, identity maintenance, and what does that really mean? Maybe we'll talk more about it later. That motivated and finally manifested itself in some of my more recent work. My very first research project when I was a young student was in complex creative systems. A biomedical engineering professor, Joe Tranquillo, inspired me and guided me to look at what does it mean to build dynamical systems, self-organizing systems, and can we get them to do something interesting? We looked at, can we create new food recipes? That was really hard. Obviously, I did not succeed, but I learned a lot in the process. I learned a lot of interesting historical approaches from those that worked in like the Santa Fe Institute and also pair box sandpile model, all kinds of wonderful, interesting bits of algorithms that I was exposed to. That motivated me to try to build systems that could self-organize or systems that could arrange their parts in a way to tackle problems, to adapt in a niche. And then I guess the last piece to that is not too long after that project, I went to grad school and I got exposed to Hopfield models. And we know recently John Hopfield won the Nobel Prize. And I also studied Boltzmann machines. I looked at some of those particular models, and I was always fascinated by this idea that they were limited. I actually found it interesting that a Hopfield network, the classical model, could only store so many memories, and then it would start forgetting, and it would forget in a very gradual, graceful way. I always thought that that was interesting. The fact that it was limited, what could we do because of that limitation? That felt very human-like. The notion of memory also became another part that got interwoven in my path. And so I think those three particular little bits motivated the work that I would do later in grad school and beyond.
So we're already talking about possible comparisons and possible disanalogies between artificial intelligence systems and what might be going on in the human brain. Your university webpage says that your labs develops new computational architectures that embody various properties of biological neurocircuitry. Maybe we can talk about neural networks, whether it's Hopfield models or other neural networks. We have neural networks in our own biological brains, and most people understand that modern AI systems have something similar with networks of artificial neurons. How far does this similarity actually extend, and should it be extended further?
That's a really good point to bring up in terms of what is the differences and similarities between what we call today artificial neural networks or deep neural networks or deep learning. A bunch of these different phrases come together to basically say that when we build what's known as a neural network, these multiple layers of processing of data or information that we can somehow transform. We take an image and we turn it into like a grid of pixel values. And then we basically run it through what looks like a big graph. Information runs along these little edges that we represent with scalar numbers. And those are the strength of a synapse. And that's supposed to mimic a synapse or a connection between any two neurons. The higher the value it is, the stronger the memory, the more persistent that information is, the more likely data might go along that path if it stimulates it. And then we have neurons in multiple layers that these synapses or connections connect. And in deep learning, they are effectively these little points that basically take multiple synapses that carry signals along them. It's like a weighted combination of values. They sum them together, run them through some other little function that we call an activation function. And that's pretty much it. We build multiple layers of these little point-wise connected edges to build some massive structure. We might do some other fancy tricks, but at the end of the day, we're building big piles of these points, arrows and dots, and they will eventually make some type of prediction. Maybe we have some function at the very, very tippy top of this network. And what it's trying to do is says, oh, the output, these very specific group of neurons or points that you have in your deep network, they make a prediction. Maybe they're trying to guess, for example, is this image a cat or a dog? And then my scoring function says, was this correct? Did you get it? Is it really a dog or is it really a cat? And then basically you sort of punish or you negatively weight some aspects of this network to say, hey, you guessed wrong. It wasn't a cat. It should have been a dog. And I would like you next time when you see that same data point, predict it to be a dog. That's kind of like deep learning, roughly in a crash course nutshell. And that's what's really powering most modern AI systems. Oftentimes, the big backend, the learning part of AI is known as machine learning, and these deep networks sort of characterize it. And so what I just described are artificial neurons. In biology, the concepts are very different. Just even from the picture that I presented earlier, where I have these little points that take weighted signals, a real neuron is inherently dynamic. It's inherently temporal. The idea is that you can say it has a neuronal dynamics, that it changes with time. Even if that neuron is not receiving input, it is essentially flowing. It is following some type of flow, if you want to think of it like a liquid through time. It's essentially stateful. It has its own little memory. So already right there, the computation inherent to a little neuron in a biological system, or even anything that tries to mimic that, is already different than a pointwise neuron in deep learning, where effectively, as I joke with my students when I teach them, it doesn't exist until data is run through the network. Whereas real biological neurons or biomimetic systems that try to mimic that, they're always on. That's already right there a picture in how neurons dynamically change with time. There's also in the brain something really important. Your wired network of neurons communicate with what's known as pulses. Whereas in deep neural networks, you have these real values, and basically they are cascaded or pushed through all the layers of the network once you give it data. Whereas neurons in the brain are really inherently called spiking neurons, and they basically communicate with these little on or off signals. The idea is that any single neuron, again, because it's inherently stateful, it has those dynamics I described earlier, builds up an electrical charge or an electrical potential, to simplify it. And when it reaches a certain threshold, then it'll fire a pulse. Otherwise, it doesn't do anything. It's quiet. It'll also rest. It'll get tired. Also, by the way, the fact that these neurons communicate with pulses, they produce these very sparse patterns. When you take an fMRI scan of the brain, you don't see all the neurons light up like you would if you were to look at a modern day deep neural network. Another joke I make when I teach students deep neural networks is I say, if your brain was like a deep neural network, that means all your neurons are firing at every single instant. You would really die. And that's an incredibly energy intensive process. So those real valued numbers that are constantly being pushed through these very, very big networks, and they're only getting bigger today. We could maybe talk a little bit about transformers and large language models and all the rage, ChatGPT. But when you're thinking about real biological neurons and connected systems of them, they're communicating with very, very little resources. They're kind of just these little pulses connecting through the network. Also, synapses are more complicated. We could talk a little bit about that if there's interest. They're not just those little weighted edges. They're compound. They have a tree structure, a dendritic tree structure. That means that they can also integrate a lot of very nonlinear information. And then I guess the last part I will add to this picture is that in real biological systems, you have real distributed parallel processing. Any single grouping of neurons or any particular neurons in the system don't have to wait for others to do their computation. It happens in this instantaneous, asynchronous fashion, which is very difficult to even partially emulate in deep neural networks. Again, that means that we're going to have this problem that we can't easily do parallel computing unless you hack a neural network to make it work the way you want it to. And then there's also the gross energy inefficiency. And then also, we could talk about this if you want. The learning process is also dramatically different in the brain. So there I was just talking about physical properties, the structure. I guess the quick point is when you train a deep neural network like you do today, you're using something called backpropagation. You're using essentially calculus to take that loss function I described earlier and calculating derivatives of it and then chaining those backwards along the exact same path you ran data through the network. Whereas in biological learning, you don't get that process. It doesn't work like that. You basically have this notion of local learning. Synapses have all the information they need, usually through chemical traces and the signals that were propagated through them. They can already adapt to them in a very local fashion. And that's also very alien and very different than the way that we would do modern day AI through deep learning.
So, Alex, the $64 million question is, why is the brain so much more efficient? A human brain operates requiring the energy of a light bulb, and it takes the energy of New York City to train GPT-4 and takes quite a bit to just run it. Why are brains so much more efficient? You referred to spiking networks. That is an idea that lies behind an alternative kind of computing called neuromorphic computing, which I guess you're probably involved with.
Yes.
Do we know why brains are so much more efficient than large language models, for instance?
I think there are maybe two parts to that, and there could be more that I'm not even properly capturing. So one is sparsity. It's that fact that we are communicating with these discrete pulses and that there's a parsimonious nature to the way that computation happens in these biological or biological-like systems, where you only calculate things across a pathway that is absolutely needed, and we sort of reduce the amount of what's needed in a particular calculation. Not all the neurons need to play a particular role when processing a particular sensory input. If I show you a picture of a cat, not every single neuron in your eye circuit, for example, is processing it simultaneously. That also reduces the amount of computational resources, if you want to call it that. That's also where energy is expended when we're doing this compute. If very few neurons light up in response to a particular pattern, then that's a good thing. And biological systems, thanks to evolution, have optimized with that in mind. Because again, there's a metabolic cost associated when neurons process information. And obviously, we want to get the most bang for our buck with the substances that we consume, our materials. We're converting matter into energy. This is kind of an inherent notion that drives biological intelligence. I think the other part that's interesting is when you think about what biological neuronal systems really do, they're working with this notion of in-memory compute. In-memory computing basically is saying that I want to do computation as close as possible to where my memory of data is. You don't want to have this big transfer like we do in von Neumann architectures like we do today. When we use a computer, even our laptop, and even most systems, even GPU systems, there is this inherent, I have information like the weight encodings or the weight tensor values in long-term memory. and I want to transfer it across different subsystems of memory. And I must go through RAM, random access memory, all the way up till I get to the CPU in order to do my actual calculation. I obviously need to move data. I need to move parameters of my network to an actual processor to do some floating point calculation. And the floating point calculations are not that energy intensive as compared to all this memory transfer. So basically, in any von Neumann architecture, and you could just say any standard computing architecture today, we are expending all this energy, joules and joules of energy, picojoules, in fact, going across different memory subsystems until we reach the CPU. And then we execute our code for our deep neural network programming. Now, in memory compute systems, we don't have that transfer cost. That means that when we think about any particular neuron or a particular unit in maybe a memory grid, that thing will do its calculation on the spot. Now, it has its own localized memory, its own asynchronous compute, because it's not necessarily chained and waiting for other neurons to do, or other computing units to do their thing. That's going to give us this really powerful property that the energy that we're using is just for those floating point calculations. My friend Carl Friston and I recently talked about that what this in-memory compute really does is it puts you as close to the substrate as possible that executes that compute that you want to do, like process some information. And so that reaches what's like a thermodynamic bound. The bound that you want to reach is there's a certain minimum amount of energy and heat dissipation that is needed to change a bit on a computer, erase or write a bit. There's like a physics bound. This is the absolute lowest cost that we can ever get to. In biological systems, now this part I don't have necessarily a clear-cut answer. A neuroscientist might be able to speak to it, but it is much closer to that bound. I just don't know how close to that bound as compared to our traditional computing architectures today, which have that, what I was implicitly describing as the memory wall or the von Neumann bottleneck. Because again, any traditional architecture today, especially those that are like the transformers, are inherently going to have to deal with this memory transfer cost, which is a huge, huge sink of energy, and basically is one of the reasons why they have such big carbon footprints.
But transformers are coming up with the results. What you've described seems theoretically to be a much better system, but in reality, the world is running and running with deep neural networks because it's apparently able to do so much, although it does have energy-intense implications. Can you point to any experimental results that would back up the kind of architectures that you have in mind?
If we're going to talk about what the results of transformers are and what might be their limitations, I'll pick two types of problems. There's a couple other ones that are out there. One is this problem of a sparse reward signal, and the other problem is known as catastrophic forgetting. This now tackles more like their generalization, their behavioral properties, as opposed to the energy arguments that we just dived into earlier. The sparse reward for the audience, by the way, is just this notion that when a system, an agent, a computer system, or even an organism takes actions to solve a problem or play a game or do something, they follow this pathway to get to their goal. And then we give them a positive signal. Like, for example, I give you a cookie if you made it to the goal, and if you didn't, I slap you. There's a positive and a negative reinforcement depending on whether or not I like the actions or series of actions that you took or not. Did you reach the goal? Did you accomplish the task I wanted? And what makes that sparse is you don't get that signal, that positive or negative reinforcement, until you literally reach the goal. You don't get anything along the way. Now, there's different versions of this notion. This is also a big problem in reinforcement learning. But anyway, the notion of getting to these goals is very difficult. What my lab has worked on over the past couple of years, particularly in the space of robotics or neurorobotics, is can we take these biological systems, or let's say a biomimetic approach? All the things I've been discussing are like properties of actual biological neurons. And then what we want to do, as Callum also mentioned, we take neuromorphic systems, which are inspired more strongly by those biological principles. And then can I actually tackle problems like sparse reward signals. And so we've built these, what we call little cognitive architectures, which are modular systems that take these biological neurons and they learn in a way that doesn't use backpropagation. So they have all this nice parallel computing. But if we go back to my earlier comment that I said neurons are inherently stateful or inherently dynamic, which is very unlike most modern day deep neural systems, you get this nice property of memory that helps the neural network. And we've shown in our work that these kind of memory conditioned modular systems that also take further inspiration by organization of the brain. Our brain has different forms of long-term and short-term memory. They have different subsystems that learn to turn off and turn on things, like we have the basal ganglia. And some of my friends and I argue that it's like an information router that learns to depress and excite different regions of the brain. If you emulate these at a high level and you use the tools that biomimetic systems bring to the table, we have shown positive results on tackling the sparse reward problem. It's really nice because then you get elements of that efficiency that we were just talking about earlier, because you're inherently not using a backpropagation, deep learning based approach, but you're using these biomimetic kind of neuronal systems. And so we show better results, or at least good results, compared to the inefficiency of modern day neural networks. And you can learn faster too when you build these little neural cognitive architectures. And then the other part that I think is really cool and worth highlighting is catastrophic forgetting was the other problem I mentioned earlier. Deep learning faces this problem, and despite what some might say, I still consider it largely a grand challenge and an unsolved problem. The idea is that when you take a neural network, let's say a deep neural network, and you train it to predict cats and dogs, it gets, let's say, 90% accuracy, or it does really well. And then I take that exact same neural network and I continue to train it on, let's say, cars and trucks. And I want it to distinguish between those. So now it needs to be able to predict cats and dogs, but I'm never going to show it another image of a cat or a dog ever again, or at least for a long period of time. I'm going to just show it trucks and cars, and it learns to predict those. It gets about 90% accuracy. If you take that same neural network and you say, okay, now let me show you an image of a cat or dog, it'll completely do poorly. It'll get abysmal generalization performance. And this is this notion that it has forgotten or overridden all that knowledge it had acquired about cats or dogs as it's trying to learn about trucks and cars. This is inherently a big problem, and all kinds of variations to this issue. What my group has shown is that, again, by taking that inherent statefulness of neurons and also taking advantage of other nice design properties that freeing yourself from a backpropagation based approach kind of locks you into, you can build nice little neuronal mechanisms that improve memory retention. So then we can show, for example, improved performance on catastrophic forgetting. Like we can train a cat and dog detector, continue training it on cars and trucks, and maybe even mix in some other things. And we show that there is this nice little robustness property when you're working with these biologically grounded or more biomimetic systems. That's a really, really interesting property. And it highlighted something else that my group has long argued, that the way in which we approach deep learning today, using, for example, backpropagation, which kind of is almost silent nowadays, it's just like the popular workhorse that everyone uses, even when they're building their big systems, there's constraints that that algorithm introduces. They sort of constrain what you can and cannot design. You need, for example, a particular system that doesn't have these loops, which in the brain, there's a lot of recurrent loops that allow you to store memory. You have to be very careful on how you design your architecture so that way you please the learning process itself. And then there's other things about backprop, like it's going backwards along the same pathway. So you better construct a good pathway so those information signals don't disappear when you're moving along it. Whereas biological approaches don't have those issues, and you can show that they actually free you up in terms of design choices that you can make. So that way you can construct an architecture that's even potentially better for certain problems that you want to solve. Like, again, catastrophic forgetting. We can introduce nice little memory mechanisms without worrying, does it please backpropagation?
So is it your prediction that companies like DeepMind or OpenAI or Anthropic, they are going to hit a wall, that they're not going to be able to keep on improving until they adopt some of the neuromorphic ideas that you are talking about. Might they be able to tweak their systems to copy some of these elements, or do they have to go back to a bigger rewrite to get the significant improvements?
Also, can I just add, are you actually working with neuromorphic models, Alex? Are you developing neuromorphic software and hardware?
Yes, mostly on the software side at this point. But yes, we are collaborating with individuals that have access to those neuromorphic chips. I work on spiking neural networks as well. I consider them one of the most promising biomimetic systems. So if the answer is yes to your question, to David's question, I completely think so. I think that we will be hitting a wall over the coming few years. It's not clear to me exactly when that wall will come up. I think the energy problems might highlight some of the issues sooner rather than later. But I think what will end up happening is that companies like DeepMind and Anthropic will find that just scaling up the number of parameters, because basically the idea is that bigger is better. If I just add more parameters and I have better resources to execute all those GPUs and CPUs or TPUs, maybe even like some say, I need a nuclear power plant to now start powering my transformers, which I think is in the really wrong direction. But again, if we want to just make that bigger, we're going to see intelligence emerge. That's highlighting a direction that we'll just eventually find that we're going to get really good narrow AI. And narrow AI for the audience is artificial intelligence or intelligent systems that are good for a particular problem or a task. And I do think that we'll make some progress in certain applications, although I do believe that the applications of these intelligent systems come a lot from still the human ingenuity and the clever design of the application itself, rather than from the large language model or the transformer. So if we want to get to more general purpose intelligence or more powerful, more robust forms of intelligence, we are going to need to consider that, like you sort of implied earlier. It might mean that we can still use pieces or building blocks that we've used in deep learning. I don't think everything needs to be thrown out from scratch. A lot of deep learning is, for example, built on linear algebra. There's just a lot of linear transforms that we can take advantage of more efficient implementations of them. We can work with, for example, sparse transformations. There's been a lot of long work on that. And I think we can rearrange some of those building blocks to build biomimetic systems. But I do think that there needs to be a move towards more biomimetics. One direction that we could talk more about later if you want is mortal computation, going in this very, very specific future direction. But in the short term, I do think something that you said is important. Can we tweak these architectures, or can we tweak these systems to get some of the benefits? And I think maybe there is a little bit of that. The big consideration is, can we train some of these systems that we think work really well on a narrow problem without backpropagation? And what does that look like? And there has been some work. I have friends beyond my group and other colleagues that have shown, for example, you can train a transformer with something known as predictive coding, which is just a very specific form of learning. You can train these systems without backprop, and you can get similar performance. I do think that that's more of like a temporary solution, but that can help maybe induce a transition from our locked view of how we do deep learning today towards something that's more biologically grounded. And then we can take advantage of the stronger properties that come from freeing ourselves from the traditional deep point-wise neural network that I described earlier.
So, Alex, you've talked about a lot of fascinating things, but do tell us more about mortal computation. What is mortal computation?
Sure. I'm glad you asked. That was some more recent work that came out at some point last year with my friend Carl Friston, who's a neuroscientist. Mortal computation, if you trace it back in 2022, end of 2022, my friend Jeff Hinton had this phrase in one of his papers where he was working on a different biological learning process. And he and I were talking over email about some of that work. And I was working on that. And that was an interesting direction. And he introduced in like a paragraph, what is mortal computation? It's this idea that software and hardware cannot be easily divorced. That again gets into analog computing and what real biological systems like ourselves are. where the computation cannot be inherently separated and executed across different platforms. If you think about your mind and your personality, that would not necessarily work if I transplanted it in a different body. There's a lot of grounding in your own body. He was just mentioning this very simple idea that that's the difference between energy efficient systems, but there's also digital intelligence, which is immortal computation. We can execute our program independently of the substrate, and it doesn't matter. And that was like just maybe a couple of sentences. So I decided I wanted to write more about that and expand it out. And so what Carl and I have done is we've said, well, actually, mortal computation is really another corollary of something called the free energy principle. And you can just say that's a really interesting idea that unifies all of life and all of agential intelligence. But really, it just means that when we think about your cognitive functionality as inseparable from your body, from your mortal system, then this is something that actually gives you the basis for real biomimetic intelligence or very general intelligence. And so we kind of started to take that and push that in a particular direction. And this is where it connects to what I mentioned earlier, my fascination with identity and identity construction. So the free energy principle and mortal computation, what they really try to say is that the inherent objective of any intelligent system, and it could be as simple as a very, very, very simple organism like a bacterial cell, all the way up to a complex entity such as an animal or a human, is that we do not want to die. And the idea is that ultimately our goal, whether we're conscious or not about it, consciously thinking about it or not is a different story, but we do not want to disintegrate into our heat bath. We do not want to lose our identity. That is our inherent objective. And everything that we do is in service of this particular objective. Now, this doesn't speak to very complex cognitive functionality. This does not speak to consciousness. These are cans of worms that I'm not touching, but they're like this base foundation for sentience. And you can now cast everything as following a gradient flow of variational free energy. This is trying to say I want to reach my self-organizing state such that I do not disintegrate, that I persist and I acquire resources so that I can continue persisting and staying organized and stable. And this speaks to the anatomical, biophysical composition of what you are. And then you can't also just think about the notion of your body, but you must also consider the fact that the environment shapes what you are as much as you shape it. There's a bidirectional inactive element to this notion of intelligence. And then we can also speak to embeddedness, which is your connection to other mortal computers, other entities, that we have cultural and societal constraints and norms and constructions that influence us. And then we also have tools on affordances. So we interact with non-mortal entities to solve our problems. And so this unifies it from a cognitive point of view. So mortal computation, you can distill it to that instead of just thinking only, oh, well, we need to design our software with whatever the properties of the hardware we want to work with in mind, such as a neuromorphic chip, I think that it also casts this fundamental objective that you want to persist in. And so everything you do is ultimately to acquire resources to continue persisting. That opens up an interesting recasting of sentience, which can serve as a foundation for perhaps more general intelligent systems.
I'm curious that you're happy to tread into the area of sentience, but you want to run away from the idea of consciousness, as far as I can tell. Aren't they very close? Perhaps consciousness is sentience plus self-awareness, or perhaps something else. They're very close concepts, aren't they? Why do you find one something that you can meaningfully do some research in, and the other something that is terra incognita and there be dragons?
Well, it's probably because of my personal exposure to theories of consciousness. Again, it could just be my particular view. I see sentience or very primitive forms of sentience as like a platform, a foundation upon which, like you just said, I like the way you presented that, sentience plus self-awareness. I think the problem is that there's a lot of different theories of consciousness. And one of the things I learned in my early studies of consciousness is that when one comes up with a really interesting theory, it has holes. It has these problems that it can't address. And then someone will say, okay, that's great. Let me come up with my theory to address your holes. And they introduce new holes. Basically, we get this beautiful tapestry of different forms of consciousness that ultimately, the way I learned, or at least one of my professors a long time ago once told me, if you leave this classroom more confused than when you came in, that means you're making progress. Because it's such a controversial and complex topic, that's personally why I try to sort of avoid it, because there's a lot of interesting theories, but I don't know which one is quite correct. And I don't think you need to necessarily directly address what exactly is consciousness from this computational, implementational point of view to get systems that are useful and interesting. I do think we ultimately do need to tackle it. I just don't want to claim that mortal computation, that particular corollary of the free energy principle, speaks to all of that, when there's a lot more people that are also much more informed and have thought about this problem a lot longer and far more brilliant than me to deal with that particular self-awareness entanglement or strange loop, if we want to use a little bit of Douglas Hofstadter.
Have you come across the work of Mark Soames, who is a close colleague of Carl Friston? They're both actually advisors to the company that I'm a co-founder of, and David is an advisor of, a company called Conscium. Mark is developing agents which he thinks could well go on to display primitive levels of sentience. And Carl obviously is working with him on that. Have you come across that work?
What's his last name?
Soames, Solms.
No, I have not, but I will look at Mark's work.
There's a very good book called The Hidden Spring he wrote recently. Comprehensible, even to lay people like me.
Sounds great. I'll check out the book and look at his work. I think it sounds interesting, and maybe a tool to help advance some of Mark's ideas could be mortal computation. I like the way that you presented what he was saying as a primitive form of sentience or a primitive form of consciousness. And I think that mortal computation serves as a framework. Also, by the way, I want community contributions. I want more people to work on it. I think it serves as the springboard for a completely new domain, a new discipline of research that I think brings in physical computing, neuromorphic computing, biomimetic intelligence, and bionics. And I think that could allow us to attack, for example, building systems that have some rudimentary form of sentience or basic levels of consciousness. I think it's kind of important because it even gets at this notion of proprioceptive behavior, understanding your own internal states and using that as an objective to drive you. I think it's just, even if nothing else, a good way of starting to think about how we design agents in complex systems. So Mark's work sounds wonderful.
Going back to neuromorphic computing for my last question, it's an idea that's been around for a long time. Carver Mead first proposed it in the 60s or 70s, I think. And there's been some quite serious attempts to create neuromorphic computing. IBM and Intel have both had a go. It's obviously very hard. Do you think that in the next few years, neuromorphic computing is going to become, if not something that replaces von Neumann architecture, at least an important platform going alongside it?
It's a good question, although it's hard to make predictions of the future. I would say I'm hopeful, so I'll give an optimistic view. I don't think it will replace deep learning, at least not in the foreseeable future. I think maybe in the next couple of years, we're still going to see advances and pushes being made for at least what I call the narrow intelligence move with deep learning. I do think that as energy concerns become greater, we're going to care more, or hopefully we will start to be motivated more strongly to care about green AI, which is something else Carl and I highlight in our work on mortal computation, which is moving towards energy efficiency, moving towards in-memory computing, trying to get to that thermodynamic bound that I highlighted earlier for basic computation. I do think that neuromorphic computing offers a very promising way to execute in-memory computing. And I think as the pressures of climate change start to get more severe, and depending on what political situations might exacerbate that problem, maybe there might be a stronger push for this. I could foresee that happening. So I do see that working in development, making progress alongside of it. Something else that's been more recent and I think is promising is dynamic vision sensors, or DVS sensors. which are like this event-based, spiking-driven way of processing information. And I think those seem to offer an interesting way of processing sensory information that's inspired by biological vision and more grounded in it than, let's say, our traditional cameras. Those seem to go really nicely with neuromorphic chips. Obviously, they fit within the theme of energy efficient sensory processing. And I think those will be helpful going forward. There's some interesting work across different groups I see. Maybe if those get highlighted more, that might be important. Based on discussion with individuals that have even worked on neuromorphic chips far longer than even I have, I think the thing that we still are missing in the domain is that killer app, as they would say. We're missing that big application that really, really strongly highlights that this is what neuromorphic can do that our traditional energy intensive deep learning systems cannot. Showing that in a chip might be the most important thing. I personally think the place to really be working on it is robotics. Robotics is that most sobering domain. My group contributes to neurorobotic control. We've gone to ICRA, for example, and other really nice robotic conferences before. And I tell my students, if you really want to know the state of artificial general intelligence, go to a robotics conference and see how hard those problems are. Making a cup of coffee or picking up an object and moving it from point A to point B is still really hard, especially from a general intelligence point of view, today as it was many decades ago, despite all the wonderful progress being made in robotic control. And I think robotics is going to be the place where not only does the energy efficiency really matter, I think also it's a beautiful platform for mortal computation. I think that's an in silico way of instantiating the stuff we were talking about earlier. That's where the killer apps might need to come from, trying to make a big advance in some really difficult robotic problem. And I think neuromorphic computing brings a lot to that. And I think that that's a place that maybe we need the field to consider more strongly. I could be proven wrong, but I don't think neuromorphic computing will go away. I think it'll always be there waiting for us, welcoming us in an embrace of saying, oh, okay, you've reached those walls. We're out of options. Well, here we are. So I also think neuromorphic computing, people like myself and Carl working in biomimetic intelligence, mortal computation, all these frameworks and ideas and tools, everyone working on those, I want to comment to those in the audience too, keep working on it. We'll welcome everyone else when they're ready for it. So I think at least within the next decade, we're going to see some stronger interest in these technologies.
So we ended up with killer robots, but at least it's a different kind of killer robot. It's robots that demonstrate the killer use, a wonderful, inspiring use of the technology. My final question to you, Alex, is you said you welcome contributions. Where can people find out more about this? Should they be reading the paper that you and Carol produced together on mortal computation, or is this something perhaps more accessible?
Certainly. If you want to learn more about a future direction and those discussions we had earlier, look up the paper, Mortal Computation, a Foundation for Biomimetic Intelligence. And it's a 40-page review of lots of more brilliant people than I could ever hope to be talking about these ideas. So over the last several decades, that would give you basically the framework for that directive that we were talking about with a lot of references. It has, I think, 500 references in there, so lots of other work to connect to. Another one, if you're more interested in how do I build non-backpropagation based neural circuits or neural intelligence, there is one. It's called Brain-Inspired Machine Intelligence, a Survey of Neurobiologically Plausible Credit Assignment. That one's a fairly long review. This was written as a particular bit of work to try to highlight the last several decades of biological credit assignment, which I felt has not been done justice. And I think unifies them in a taxonomy. It's meant to be pedagogical as much as it is to be inspiring for future scholars that want to contribute. If you're interested in anything that isn't backpropagation, I highly recommend that. There is a shorter version of that survey, like a sampler, and I'll mention that here as well. It was also meant to be pedagogical. It's called a review of neuroscience-inspired machine learning. And I did this in collaboration with a couple of my collaborators and good friends. If you don't want to read a 50-page review of everything that's ever been done, this one gives you the 7 main algorithms or 7 main ideas to get you started. And I highly recommend that people look at those resources and read them. They were meant to try to give you as much comprehensive touch of everything that's been done. So then pick your favorite part and then work on that, because we need more people to work in that space. And it also has connections to neuromorphic computing. And the last shameless plug I'll make is that if you program, if you work with maybe the Python programming language, my lab has a tool called NGC-Learn. And if you look that up, it's a free public open source toolkit that allows you to do generic computational neuroscience modeling, biomimetic intelligence. Basically, again, if you want to work hands-on with the tools that my lab and others do for non-backpropagation-based approaches, you can also build spiking neural networks. If you're fascinated by simulations of models for neuromorphic computing, our lab is actively pushing to build connections, for example, with Intel to try to build a bridge to their Lava platform for their Loihi chip. I think that that's really nice. We also warmly and strongly encourage community contributions, because another goal of that tool, NGC Learn, is not only to give everyone a tool for education and research in computational neuroscience and biomimetics, but also to allow you, for example, to reproduce historical work. We have a little museum that reproduces historical papers so that you don't have to struggle finding someone else's code. You can just start building or using other people's code in there. And we would love others to contribute their work if they use NGC Learn.
It all sounds like great resources. Perhaps there's a scope for a dummy's guide to mortal computation at some stage. But for the time being, there's lots of things for our listeners if they wish to get their teeth into. Thanks very much, Alex. You've been a fascinating guest on the London Futurists podcast.
Thank you for having me. It was a pleasure to be on.
Thank you very much for joining us, Alex.